It is my great pleasure to introduce Dr. Professor Ramirez this morning. Now, most of you probably know Professor Ramirez because she hosts Science Saturdays. What you may or may not know is that Professor Ramirez imagined, invented, and created this program, and a huge amount of blood, sweat, and tears went into actually making this happen. So for all those of you who enjoy it, we should start by giving Professor Ramirez a hand. Now, besides being extraordinary and creating and running this program and making it happen every term, Professor Ramirez is probably one of the best scientists that I have ever had the privilege of knowing, and a really fantastic researcher. She is going to be talking a little bit today about some of the research she does, so I'll let her take care of that. But one of the things she may not talk about is that she's also a phenomenal teacher. She has one of the most popular classes in engineering, and she's in fact essentially recreating a field in engineering because everyone wants to keep taking material science after they go to Professor Ramirez's class. So she's a fantastic teacher, an amazing scientist, and we'll get to see a little window on that today. Besides all of that, she's also one of the great mentors here at Yale. She really looks after everyone, and she's a phenomenal friend, and we're very, very lucky to have her. So with that,
thank you very much. What a great introduction. I'm done. I think I'm done for the day. Well, today I have the opportunity to sit on the other side of the podium and talk to you a little bit about some of the research that I'm doing. So my talk is entitled Metals with Memories and Other Smart Materials. I think the best way to get started is actually to show you this at work. So let me just get some hot water here. If you can look at the, oops, sorry. This is going to take a little bit of adjusting. Look at the side things. All right, so we have some hot water. And what I'm going to do is I'm just going to show you this wire, which you may be familiar with already. This wire right here. Can you see that? Okay. Now all I'm going to do is wrap it around my finger so there's no magic. You can see it happening in real time. And I'm going to slip it into the water. All right. So I'm done with my talk. Thank you very much. All right. So what I'm going to do today is I'm going to talk a little bit about why this material does what it does. All right. Why does this material remember? Now, what did we see? We saw the wire, I bent it, I heated it with hot water, and it went back straight. So today we'll talk a little bit about the mechanism behind what's going on. What are the atoms doing? Now, before we get started, this material does have a name. It has an official name. It's called Nitinol. It's not the most creative name, but it actually tells us quite a bit about the material. The first part of the name, Ni-T, it tells us that the material is made out of nickel and titanium. 50-50, equal amount. The second part, Nol, that tells us where it was made, in a small laboratory in Maryland. All right? So there are many names that this material also has besides Nitinol, and I'll kind of use them interchangeably, but you may hear me say shape memory alloys, memory metal. You'll also see muscle wire, or SMAs, which is just an acronym to say shape memory alloys. So this is the material that we'll be talking about today, why shape memory alloys do what they do, what you just saw a moment ago. Now, before we get started in talking about how they change their shape, we have to talk about atoms. No, not atom. Atoms. This is what I mean, atom. All right. So, atoms, we all kind of have an idea of what atoms are about. They have a positive core with the neutrons and the protons. Circulating around them are the electrons. Well, we don't need to go into that much detail into understanding why materials do what they do. We can actually step back and look at materials more from billiard balls, from hard spheres, right? And so billiard balls or oranges, they all kind of have this circular shape, and they also have some kind of organization. They kind of order themselves in certain ways. Well, atoms as well order themselves, and we'll talk about that in just a moment. There's a few ways that atoms can order themselves. There's actually 14 of them. They're called Bravais Lattices. Can you say that, Bravais Lattices? Bravais Lattices, exactly. See, when you find something, you can name it after yourself. All right, and so the thing is that the material that we're interested in uses two unique structures. Cubic, which looks like this, just a cube, all sides the same, all angles are 90 degrees, and also monoclinic, which looks like this. Yeah, I'll pass it around if you want to look. right? Just so you can see. I always describe monoclinic to look more like a pink eraser, that kind of shifted shape, right? And what happens is that at higher temperatures, atoms of nickel titanium like to be arranged in this cubic arrangement, and at lower temperatures, they like to be in this monoclinic arrangement. Now, these different arrangements also have names because, once again, when you find something, you can name it after yourself. So high temperatures, that's austenite. Low temperatures, that's martensite. All right. So when we just saw a moment ago this wire that was bent, and that when we heated it, it became straight, what we were seeing on a macroscopic level is what atoms are doing on a very, very microscopic level. That is, they're changing from martensite, when we heat it, to austenite. All right? So atoms, these very small entities, 10 to the minus 10. That is, if I were to, your hair is about 100 microns. If I were to sit on a stoop and whittle a piece of hair 10,000 times, one of those shavings would be the thickness of an atom. So it's that scale that's impacting the material that you're seeing in forming austenite. Well, how are these atoms doing this? Well, there's essentially a parade. Have you ever seen a really great parade, but those really sophisticated ones where they're starting to move in different ways? Maybe they have some really great music playing. That's what the atoms are doing. They're shifting around, and they're creating a new phase, a new structure. Here's a way to kind of just see that another way. We're seeing that these atoms are shifting from martensite to now austenite. Martensite back to austenite. And all they're doing is they're just doing this by a simple shift. Two different materials, but just by a simple shift. And that's what's so great about these materials. Well, I think I want to really get this message home. So why don't we try this out? This computer is a very smart computer, has a mind of its own, actually. And what we're going to do is it's going to flash red, and it's going to flash blue to indicate that we're cooling or that we're heating. All right? And when we're cooling, we're forming martensite. So we'll all put our hands this way, all right, to the side. And when we're heating, we're forming austenite, which is a cubic structure, and so we'll put our hands this way. Very good. All right, so let's see what the first one is. All right, this way. Brilliant. This way. This way. Oh, it's the wave. Great. Fantastic. All right, so you see this process of going back and forth. Great, great. Boy, we're on fire. All right. So this small shift is what the atoms are doing. Now, I mentioned this word phase a couple of times to describe austenite and martensite, and I think I should be a little bit more clear about those things. So what is a phase? Well, there's a couple of definitions. I kind of did a survey. One, it's something that you're going through, something that annoys your parents. And lastly, it's a distinct form of matter, and we're familiar with a few of them. If we have states of matter such as water, we know that it exists as gas, right, vapor, liquid, right? And what's the solid form again? Ice, exactly. So those are different phases of water of the same thing. Here's an example of two phases existing at the same time. I have a beaker where I'm heating water, and I have two phases present at the same time, the liquid and the vapor. So we can have two different phases based on state. But we can also have materials that are the same state, like a solid, but they're different phases as well. And we see that fairly commonly. Carbon can have two different phases. It actually has a way to describe carbon having two different phases is also allotrope. Can you say allotrope? Allotrope. That means that it has different phases. Now, we can have carbon in the graphite phase. You can see a picture of it located right there. We can also have carbon in the diamond phase. Very different properties, right? Do you want a pencil made out of diamond? Yes, you do, because you want to sell that. That's right. But you don't want to use it. That's right. So, but we have graphite, which is a very soft material, and we have diamond, which is the hardest material that we know. They're both made out of carbon, but the difference is that they just have different atomic structures. So different arrangements can give rise to different phases. And that's what the nickel titanium is doing. It's creating different phases, but it's just doing this by a displacive motion, moving from one arrangement to another. Now, why do I keep saying this? Why does Professor Ramirez keep talking about this displacive moment? Well, it's because most materials don't do this, that is, create different phases just by shifting their position. Most undergo diffusion. Now, if I were to go down the middle of this row here, and everyone on this side is an A atom. Hey, A atoms. That's right, brilliant. All right, over here, B atoms. B, hey, how's it going? All right, so let's say that I wanted to create a new compound, AB, right? So the A atoms are here, the B atoms are here, and I want A and B to come together. Now these lucky people right here, it's very easy for them to make a compound because they can move very short distances. However, my friend over here has to travel a significant distance to get over to the B side, right? And that takes time. That takes also a significant amount of temperature because we have to give them enough energy to do that. That's not the case for shape memory alloys. They just make a small shift and they're already they're already a different phase. So that's why I keep emphasizing this. The other thing is that only a few compounds do this. It's based on some geometrical constraints based on these different structures, so only a handful of materials do this. And lastly, this mechanism, this transformation, which has an official name, the Martensitic transformation, is still a mystery in a lot of ways, and that's good because that provides job security for me. So we can think of these materials as transducers because what we're doing is we're applying heat and we're getting force. So it's changing energy. It's changing it from heat to force. So that's what we'll think about these materials. Now, there are many uses for this material, not only because of the fact that it goes through this phase change, but also because it's flexible. So some of you may be going through this stage right now where you have orthodontics based, and it may have some shape memory alloys. You also see that these materials are quite handy in some eyewear. In fact, I have an example of one right here. So look at the camera on the side. Look at this wonderful. First, aren't these lovely? All right. So here's my glasses. Would you do this to your parents' glass? No, you wouldn't do that. You would get in trouble. What's also nice about these materials is if I cool them down, so this is just liquid nitrogen, which we love, right? No. Okay, so here's liquid nitrogen, really cold stuff. All right. Liquid nitrogen is one of my favorite things. All right, so here I am. I'm going to put this into the liquid nitrogen. Oh, this is great. This is awesome. Oh, look at that, it's stuck. And here's a spring. It's also made out of shape memory wire, which you can see, right? And it's actually kind of hard to pull. Well, I'll put this in the liquid nitrogen as well. Do that over here. And boy, is it flexible now. Extremely flexible. So I'll let you look at that, and as it warms up, you'll see that it'll go back to its original shape. All right? So very flexible. You can see it at work there. So here's some uses, not only before the phase change, but also because it's highly flexible. What other uses are out there? Well, it's also in stents. If you have a blocked artery, they put in a spring of this material, and it will open up any kind of closure. There's also some toys that are based on this, and also some robotic structures. In fact, there's a butterfly that's been moving right here. It's based on this shape memory alloy. And lastly, and most embarrassingly, underwire bras. All right, so you can imagine after you've deformed it from use, you can pop it in the dryer, it goes back into shape. So now we know what Victoria's Secret is. All right? She's a metallurgist. All right. So let's get a little bit more technical about what's going on with these materials. Once again, we saw that there's a phase change as we heat it from low temperature to high temperature, and it's changing from martensite to austenite. Now, we can visualize this change because we see the wire changing shape, but we also know that properties change as well, and one property being the resistivity, its ability to conduct electricity, also the stress in the material. These are things that also change as we go along, as we increase the temperature. And this curve represents that. See, if we start at low temperatures here, we heat, and we start to form austenite, as this dot, AS, indicates. That's the start of austenite. As we increase, we finish, and we have the end point of austenite, the austenite finish point. And then if we start to cool, we start to form martensite, and then we continue until we finish forming martensite. And this curve is called a hysteresis curve. It means that you don't go back the way you started. We all have hysteresis. I don't know about you, but when I go to work, I travel one way, and when I come back home, I travel another way. Hysteresis. Well, these materials do the same thing. And as an engineer, we want to tailor the properties. And one property we're particularly interested in is the height of this thing. How can we increase the height? Because that will speak to how much force can be created. We want to have more force. And we want to be able to tailor how we create this force. So we'll talk about how we do that in just a moment. Now, I've talked about cheap memory alloys, and they seem to be somewhat of a mature technology, but what I'm interested in is looking at these on a very small scale. These are small devices. This is a MEMS device, a micro electromechanical systems, a MEMS device. It's a mirror, and it's very small. The width of this mirror, if I look at this gold piece right here, that's 250 microns across. Your hair is 60 microns, all right? Just to give you a sense of scale, this is the eye of a needle, and you can see them. Now, these mirrors need to be tilted because they're going to move light, and we need to figure out ways to move these materials, and one potential material could be shaped memory alloys. So how do we make shaped memory alloys that are very small so that they'll be useful for these very small devices? That's the question that I'm interested in. So how do we make very small layers for these devices? Well, my pocket knife is not that sharp to shave off a little bit to get to 250 microns. So we actually use another process. It's called sputtering. Once again, think of the atoms as billiard balls. So if I have billiard balls of nickel and titanium, if I have an atom that is inert, meaning it won't form a compound with this material, and I shoot it in the direction of the nickel titanium, what will happen? Well, think of it as a cue ball hitting all the other colored balls in billiards. They will all cascade, and because of this momentum transfer, will create a raining, if you will, of these different atoms. Now, if we have a plate to collect these atoms, which we officially call the substrate, they'll slowly deposit onto this material, right? And afterwards, since the atoms are not in a specific arrangement, meaning that they're not in the cubic formation or in the monoclinic formation, they're not in austenite or they're not in martensite, we actually have to put them in the oven to make sure that they do this. So this is scientific cooking. And here's an analogy just to kind of show you that. Is everybody familiar with the notion of cake? Cake is very, very good. All right, well, what do we have to think about when we make a cake? Well, we have to worry about the ingredients, the amount of the ingredients, the oven temperature, and the time. What happens if you put a cake in there for too long? What happens? Burns, right? So these are all the things that we have to worry about. Well, once we do that, if we have all the ingredients, we worry about the texture, which will tell us, is this a dry cake? Is it a runny cake? These are the things that we worry about. And lastly, the most important thing we're interested in is its property, whether it's yummy or not, right? Well, we can make a parallel for one of the processes for how we develop materials. And that is as such, where we have processing, that is how we synthesize it, how that relates to the structure. It could be the structure of the atoms or collections of atoms that form grains or crystals. And lastly, how that relates to property, whatever property you're interested in. Well, essentially, I guess I'm a chef in some ways because I look at nickel titanium films that are very thin. I put them into a furnace and I anneal them. That process of heating up these materials is called annealing. I look at the microstructure, that is the collection of atoms, and see how those structures look, and see how they're related to the actuation properties, that is, its ability to move. So that's essentially what I'm doing. So let's look at this process of atoms collecting and forming grains in real time. So you can see in this very gray area, we essentially have an amorphous material, meaning we don't have atoms in any kind of arrangement. But you're starting to see these white dots. Those are small grains. Inside of them are atoms that have a periodic arrangement, sort of like that marching band again, but they're in a structure of austenite. And we continue to heat this material until all of that area is covered with these grains until it's fully crystallized. All right, we're still baking. We're still baking. Ding, time's up. All right, so this is baked. And so the experiment that I'm interested in doing is looking at how we can heat these materials up at different temperatures and what's the final structure look like. Well, let's look at those kinds of images. Oops. Give me some control. Here is an example of films that have been heated to different temperatures and they have different grain size. The temperatures are indicated at the bottom. 510 degrees, that's our high temperature case. 465 degrees, which is our low temperature case. If you don't recall what C is and how that relates to Fahrenheit, just multiply these numbers by 2 and add 30. That's an approximate for how hot it is. These are fairly high temperatures. Now, what's interesting is that at lower temperatures, we have very large grains. Did you see this big grain right here? You see that? That's a grain. And over here, we have smaller grains. Do you see that? Now, what's interesting is that these grains have lines in them. Those lines indicate martensite. Remember that monoclinic structure that's kind of floating around, the one that kind of looked shifted? That indicates martensite right there. So these big grains have quite a bit of martensite. However, these smaller grains at the lower temperature, they don't seem to have as much martensite. So we see already that there's a significant difference in the way that you cook these materials or the way you anneal these materials. You get very different microstructures. At low temperatures, you have big grains, and they have quite a bit martensite. At high temperatures, you have smaller grains and not as much martensite. So in terms of that process, relating the process to the microstructure, we've gotten that part done. The last part is to relate this to properties. Well, here's those curves, those hysteresis curves that I talked about a moment ago. And we're looking at those examples that I showed just moments ago, where we have the high temperature case and the low temperature case. You can see that the hysteresis, or the height of these curves, is significantly different. We have a low hysteresis curve, and we have a high hysteresis curve at lower temperatures. So once again, the object of the game is to create materials that have higher hysteresis curves. And what we can learn here is that lower temperatures are the way to go in order to create devices that will have larger forces. Does that make sense? All right, so what we're doing is we're cooking and we're relating it to the properties. And that's pretty much what material science is all about. Now, I want to change gears if I can. I would like to also talk about another material that's a smart material that might be of interest to you. It's a piezo-electric material. It's based on piezoelectricity. Piezoelectricity comes from the Greek term for piezin, which means to press or to squeeze. And electricity, well, that means don't touch. All right? And this is a transducer as well. It has properties of relating pressure to electricity. Doesn't that sound strange? I apply pressure and I get electricity. Well, that's what these materials do. I'll give you an example of this at work. Here I have a small disc made out of piezoelectric material. And attached to it is a small LED. That picture shows it right there. And what I'm going to do is I'm just going to apply impact or pressure, and this should light up. So here's me at work. Here's my little video, where all I'm doing is hitting this surface. Now, do you see it? Do you see it? No, you don't see it. It's too dark. So what we'll do is we'll dim the lights a little bit and try it again. Do you see it? All right. So all I did was apply pressure, and I was able to get this spark, right? I'm not a battery, although the matrix says I'm a battery. I'm not a battery, but I was able to get this spark. And so that's what this material is doing. That's this piezoelectric material. Now, what's the mechanism? The mechanism is such. Once again, think of those atoms. Think of these atoms having an arrangement, but not only do they have an arrangement, they also have a charge. So those are indicated there as pluses and minuses there. Now, when I apply a force or a pressure, what do? I change the structure. I change the structure so that on one side we have more positives, on the other side I have more negatives. Can you see that? And that's what creates this charge. So that's what these materials do. When I apply an impact, I change the structure has some charge to it, and so that's why I'm able to see this spark that you saw just a moment ago. And there's some piezoelectric materials that are out there. One of them is quartz. That's actually most popular. But I've recently found out that our bone has some piezoelectric. Now, that's not why you feel energetic, but it's on a very small scale. Also, sugarcane has some piezoelectric properties as well. So just to give you a sense of some things are out there. But quartz is actually probably the most dominant or the most popular. Where are piezoelectric materials, where are they applied? Well, they're often in loudspeakers. You know, you apply electricity to these materials, they move, and they cause sound waves. Right? They're also used in lighters. I have an example of one right here. Right? That clicking noise that you hear, you're hitting a piece of quartz. You're hitting a piece of quartz to create a spark, and there's fuel here which will set the flame. So this is piezoelectric materials at work. Now, scientists also do some future thinking about what to do with piezoelectrics, and it's proposed that we can use ourselves to create energy. Now, how do we do that? Well, every time we walk, we waste energy. All that energy just kind of goes into the floor. Imagine if at the bottom of your shoe you had a piezoelectric material and that you're able to store this material and into some kind of battery. Then you'd be able to charge up your MP3 player or your cell phone or the like. So this is kind of futuristic. This is called energy harvesting. But researchers are actually working on this because there's materials that will do this. So this is some kind of future thinking as well. And this is what scientists do as well. They see a material and then they look for a kind of far out application. So maybe in a couple of years we'll have such shoes. Well, we spent a little bit of time together thinking about materials. We've noticed that what's important is that the atomic arrangements can give rise to different kinds of structures and different kinds of properties. We saw that when we apply heat, we can get phase transformations, and also when we apply pressure, we can also get electricity. So I hope that you found this fruitful, and I'll take any questions if there's any opportunity.